We'll make sure to record, please.
Yeah, record. Always a problem. And so what I'm trying to do is give you an example why we need spanning tree and what's the purpose for it. Okay, so what happened? So PC0 can talk to PC2. Life is good, but maybe this is the cable is running somewhere. This cable gets cut. This interface is down. So what's gonna happen? That means PC0 or all these people that's connected to the switch and just attach one device. They're not gonna communicate with any of these LANs right here and any of these LANs over here. So how we can fix that problem? So
Run a line from switch 1 to switch 2.
So basically, we need to create some kind of redundant links, okay? Another wire, okay? So we go from here to here, so we can have some kind of redundancy, okay? So if this is goes down, so we still have an options or to go to this destination, and the same thing in here. So that's what the redundant link means. To create some kind of fault tolerance. Fault tolerance always defined like basically to eliminate a single point of failure. Now, let me remind everybody. So the switches that we use right now, it operates at the data link layer. And we know in communication deals with data link layer, especially on the switches, we build what we call what? How end devices communicate with each others on layer two. We use what?
MAC address tables.
That's absolutely correct. The MAC address table. So the spanning tree is good idea. I mean, a redundancy is good idea, but we got a problem. And now on the screen, because as we have a smart switches, but in the old days we don't have smart switches. So basically, if the spanning tree is not enabled by default, what's going to happen? Well, this PC wants to talk to this PC. He's going to send a broadcast, and the broadcast is going to be received by this switch and this switch to find out how we can reach that PC2. So if we don't have a spanning tree in place, we end up in going because PC2 is going to be on the MAC address table over here. It's going to be on the MAC address table over here. Then this guy here is going to tell you, okay, that if you want to go to PC2, you go from here. And this guy's going to tell him, if you want to go to PC2, you can go through here, and so on. So we ended up into what? A loop. The frame is going to go into a loop, endless loop. And because switches operates in layer two, it doesn't have the same mechanism as layer three. Layer three, if we send packet, what's some of the features in layer three? We have something called what? TTL. What's TTL stand for?
Time to live.
5 minutes. I got 5 minutes to live, right? Time to live. That's right. That means time to live. So the packet cannot wander forever, okay? It cannot go from routers to router to router forever, okay? So it has, as you go from hop to hop, the time to live will increase, decrease till get a zero. Then boom, we'll drop that packet. But on layer two, we don't have that. We don't have that. feature. So the only way we can stop endless frame going from switch to switch to switch, and it's not only that, because what's happening when you have the frame going from switch to switch, we have some kind of, like we call it, broadcast storm. So when you have a bad broadcast storm, basically you flooded the MAC address table, and the MAC address table is going to be changed constantly. So it gets confused. Your devices get confused basically. They're not on the same page. And that will cause some kind of denial of service. And you don't want that to happen because of misconfiguration on your equipment. Now, I can understand if somebody is trying to attack you to cause this problem. That's different from configuring, to misconfigure devices. So, to prevent from broadcast storm, to prevent this problem, well, they came up with something called spanning tree protocol. So you enable it on the switch, and basically what's going to happen when you enable it on the switches is going to, as you can see, these the three switches I just gave you an example like this, but we have a different models, different topology. Now, as you can see, we have physical links for each switch. But when we enable the spanning tree protocol, what's going to happen is the physical link is going to stay, but logically, okay, we're going to block one line. That means, as you can see right here, okay, this is blocked. So the reason why blocked, to prevent a loop. So I cannot pass any information on this line because it's logically is blocked. Now, if you, for example, if we can go, let's say we disable this link right here. Okay. So if I go here gigabit 0/1 and go, what port is that? G0/1. G0/1 and disable that one. So now, as you can see, we're gonna have the STP is they're gonna sense this link is down, then automatically we'll open this link. You see, it takes time, and this is basically, it depends on the spanning tree protocol version we use. And if I fast forward the operation right here, you're gonna see that this link is down, then we open this one and this one. So we have alternative path, okay? The minute I go back and fix it, I'm gonna go in here, go back in here, fix it, it's gonna go and correct itself, okay? Go back to the old ones. And notice it takes sometimes, because the switches by its nature, they have some kind of delay, because it goes into from blocking mode to forwarding mode to a learning mode to a listening mode. So it goes into like 5 stages. Okay. That's why in the old days we used to have a delay. And the reason why on the old days it takes about 60-second delay. And the reason why back then was slow is because nobody in a rush. We don't have what we call active base applications or real-time applications back then. We have like applications, that's fine. I mean, it takes 5 minutes. A delay 60 seconds is no big deal. But can you imagine you sending a video and it's late already 60 seconds, or you talking on the phone, you have a delay 60 seconds? Is not acceptable. That's why over the years they advance the common spanning tree into a more advanced version of spanning tree. But that's not the discussion now. The main discussion, you need to understand the purpose of STP. So if somebody asks you, what is the purpose of STP? If you go to an interview on a job and the interviewer asks you, tell me, why do we need to enable STP on the switch? So what will be your answer? Let me go to the chat so I can see what's your answer.
Redundancy
Uh,
or fault tolerance.
Somebody said redundancy. Somebody else want to say something else?
Or fault tolerance.
Oh. Who's that? He's giving me the answer. Okay. So why we need the spanning tree protocol? So the question. Mm. So we need a spanning tree.
Redundancy,
I'm sorry.
redundancy or fault tolerance.
Yeah, basically we're gonna build the redundancy, but basically spanning tree protocol is gonna preventing a layer 2 or frame loop to go into endless loop. So that's why they developed the STP to prevent endless loop. Okay. So even though I create a link in between switches, but if I don't have STP, we're gonna have endless loop. In a way, what you're saying is true to put to develop fault tolerance, but to be more precise, to build redundancy, but it's to basically to prevent endless loop. Because on layer 3, what prevents endless packet to go into a loop? The TTL. So we don't have that on layer 2. So that's why we put STP in place. All right. So that's basically the main idea. So let's see what they're going to talk about here on the slide when we talk about STP concept. So explain common problem, because I'm trying to solve a problem in redundant layer 2 switch network. So what is the problem? The endless loop. That's the problem. Because if I create redundancy on layer 2, I'm going to have what? Endless loop. So how are we going to prevent it? By implementing STP. And we're going to the question is, which is somebody didn't ask the question. Don't you see over here what you notice in here? Why will block this one, not this one, not this one? Who's going to determine that?
It's the speed. The gigabit 01 is faster than a fast Ethernet. So
Uh,
the administrative cost.
okay, that's a good analogy. But we have something else beside that. And we're going to talk about it in a few seconds. Okay. because we always looking for some reference. We need some kind of reference point. And reference point determine what link we need to block. Okay. So some of the what you mentioned is correct to a certain extent. Uh, and we're going to talk about the evolution of STP because we start with the basic common spanning tree, which is developed in the early 90s. They used to have a protocol 802.1d. Then back then, like I said, 30-second delay was not a big deal, but now 30-second delay is huge deal. Then we moved to rapid, a pair VLAN STP operate. So basically, was the standard, the industry standard, which is everybody used to follow by 802.1d. Then Cisco came up, well, this is good, but it's not going to work good. Why? And that's why we start developing more version of it. And we're going to go over that in a few minutes. And this is basically what we mentioned earlier about the redundant paths in the switch Ethernet network may cause both physical and logical layer 2 loops. So you need to understand this concept, why, okay? Why we need STP. Now, of course, later on in the slides, like I said, like everything else, when you start with the standard, there's no standard is a static, okay? We always update, we always improve on the standard, okay? But that's a different things. But the main thing is to understand the main concept, why we need STP, to prevent the loop, to build redundancy. Because if I cannot prevent the loop, I cannot make redundancy. I cannot have another leg. Because we talked about earlier of the semester, or maybe in semester 1, we're looking to build a converge, reliable, resilient network, okay? With high availability. So how are we going to do that? We need to build some kind of redundancy. One of the redundancy that we need to create, especially in the infrastructure, is we need to make a multiple link. Just if one link goes down, so we have alternative. So to do this, we need to, if we do that, the redundant link is going to cause a problem with loop. To solve that, we need STP. And it happened to me a long time ago in the 97, 98, I remember. I was at TH Harris back then. And I went to the computer room and I was doing something and I want to combine two switches together and I did not realize I caused a loop. So everything went down. So of course, when the good thing is when something goes down, you said, okay, what did I do? Oh, I put the cable in there. Let me go see what's the problem. Oh, I connected to double. I have a link. It goes into a loop. So I realize, and before it was not enabled by default. You have to go to the switch if you want to do STP. You need to enable it. Then you create redundant path. So it's very dangerous if you don't know by mistake. If you plug your cables from one switch to the other switch, and you don't understand your topology, okay, it can cause a loop. So I think we talked about enough about this problem. And that spanning tree protocol, STP, is a loop prevention network protocol that allows for redundancy while creating a loop-free layer 2 topology. This is a solid definition, okay? So this is a solid definition. If you go, because Sometimes when you go to the interview, they're going to ask you a few questions about technical questions. So you need to understand what that means. Don't give them like, and once you finish this program, sometime we expect you to answer the question intelligently. Okay. So that's really good, solid definition. You need to stick with it. STP logically blocks physical. Okay. We did not physically shut down this port or this port. Okay. It's physically that link is still there. But what changed? Logically, we shut it down logically. Okay. But it's still in there. Now, here are the questions. Like, remember what I did. Now, this is off. Then I came here and I shut down this one physically. Then we trigger this one to open. How? He knows this guy because we said this is a block. How we know this one is shut down? How he sense it? What's your answer for that? You know? You know the answer? Well, basically it's the same
Layer
concept
two.
that we talked about before. Somebody saying something?
Yeah, it's a smart device, layer two smart device. So it would detect that there's something plugged into the port.
Um, yes and no in the same time. And the reason why, let me see. Remember, like, for example, like suppose these two, suppose this is the server and this is the server, okay? And this is like a storage right here connected to both of them. I'm talking about the different, like a cluster servers. But in the cluster server, we have those connected to each other by port called heartbeat. So they can sense if something happened to the main link. Okay, they have some kind of a sense, like a signal. The minute they don't receive that signal, so the minute this guy does not receive any signal, okay, they assume something wrong with this link. Therefore, they right away they open it up. Okay, and this is basically what we call a bridge protocol data unit, BPDU. Even though this one is blocked, but still can receive what? BPDU, Bridge Protocol Data Unit. Okay, and that's why they sense it. Now we're blocking from forwarding information like frames, like data, and all that stuff, but still can receive. Let's make it assume is like it's like, are you there? Are you there to check if the other switch is still connected? And it's like every 2 seconds we send that signal. Are you there? Are you there? Are you there? The minute this is link is not there, then automatically this is will open. You follow? It's like ting 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 ting. Are you there? They receive this like little warning. Okay, and that's why once they sense this is the connection is down, automatically this is will open. You can call it heartbeat if you want. Doesn't make any difference, but that's what happened. Does that make sense?
Yes, sir.
Um, the main concept is because we have redundant link because this is how, and also you need to understand this is trunk, this is trunk, this is trunk. So because each switch connected by trunk port. So all this one physically is on, but logically we have to cut it somewhere. Like for example, this link here goes down, then we're gonna send it somewhere else. We're gonna send we're gonna if this were blocked here, then the information travel this way. Okay. So when we say this is like physical failure right here, not logical, that's physical. It was blocked here logically. Then once it sends it, they're gonna open this side here and we're gonna open for traffic to flow this direction. If you think about it, really it's like an alternative path, right? So if this path goes down, then we have alternative path. And actually, in some books, they called alternate port. So when you configure this guy here is an alternate port. Remember in my this one here, some people they call it block port or alternate port. Alternate means what? Means if anything happened here or here, we're gonna open that alternative port. Um, Okay, so this slide talks about the difference between layer 2 and layer 3. And as you see, the router use TTL, time to live. In the layer 2, we don't have that. And if we have broadcast storms, gonna mess up the MAC address table. They're gonna cause some kind of a flooded because the switch basically has the flood is gonna create inconsistent MAC address table. So inconsistent MAC address table, that frame is gonna go into a chaos, into a loop, and it's gonna cause some kind of what we call uh, broadcast storm. Broadcast storm is no good at all. Okay, because will cause denial of service. And that's one of the most dangerous attacks you can have on your network. And that's why, if you remember a long time ago, is the most vulnerable layer of the OSI model is layer 2. And that's why we implement port security, because I don't want intruder or hackers to come to my network, plug in his machine to one of the port, and from that port he can inject some kind of application to cause a broadcast storm in my layer 2 switches. So basically he's gonna, because there's a really a certain amount of memory on a switch. If you flood a lot of addresses in there and cause inconsistent MAC address table, well, guess what? People cannot access the server or whatever devices wants to access. And this is what caused denial of service. And and I can understand this one is happened in attack, but not from misconfiguration. So in order to prevent this one from happening, a misconfiguration, you need to use STP. Now you notice I repeat that so many different times because this is very, 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 very important. And that's again, without STP enable, layer 2 loops can form, causing broadcast, multicast, and unknown unicast frame to loop endlessly. And this is gonna eat up all the resources on the switches. So this is gonna be, and that's what we talked about here. Change the updates from the broadcast frame, which result in MAC address and the MAC database instability. And that's really a problem. And this can cause high CPU utilization, which makes the switch unable to forward frames. That's it. Once you get to this point, denial of service. The people plug into that switch cannot reach the server or whatever application they're trying to do. So we're gonna flood. The frame is gonna flood going into like this loop, 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 loop. Anyway, that's again same scenario. So how you prevent all this? Is spanning tree protocol. So they're talking about STA. What's STA? STA is the spanning tree algorithm. So STP is based on an algorithm invented by this guy, which is basically working for Digital Equipment Corporation. This is actually Digital Equipment was one of the pioneer in technology. I don't know what happened with them. And they created a lot of standards long time ago. Look, it published in 1985. 1985, guys. This is when the algorithm was introduced. An algorithm for distributed computation of a spanning tree in an extended land. So basically, the algorithm, they say, okay, we're going to prevent loops for okay by configuring a loop-free path through the network using strategically placed block and state ports. So the STP, like we're talking about, will block it. And that's based on the algorithm this guy wrote in what year? 1985. Golly, that's a long time ago. I don't know what I was doing in 1985. I think I was working for TND back then. I don't know.
I
And
was 9.
huh?
I was 9 playing with GI Joes.
And 85, well, back then, I don't know if we have, yeah, we used to have the 10D or TRS 80 or something like that. And Commodore 64. That's an old days. Okay, so how this is gonna work? This is the thing. So basically, why we need to do block this one here? So not this one here. So the algorithm gonna say, okay, we're gonna select a reference point. We're gonna select a switch, act as a reference point. Okay, from that reference point, then we can decide which side we need to block. You follow? And that reference point, we call it root bridge. So they're gonna elect a switch to act as a reference point or to act as a root bridge. Okay. Now, for a switch to be a root bridge, it has to have some criteria, and that's what we're going to talk about. And that's what they say here. Selecting a root bridge. This bridge basically is going to be a reference point because with that reference point, we cannot make a choice which side we need to block and which side we need to open. Okay. Um, and that's what they're talking about. This one here. No, block redundant pass is okay. We block it. We say block it. We're not blocking it physically. We're blocking it logically, and that's what say. STP ensures that there is only one logical path. They don't say one physical path. They say one logical path. And that was emphasizing on this one. The physical wire is still there. Physically, this is still there. This is still on, and this is still on. But we come into this port here and we put them in a blocking mode. We go to that interface If we go and see the status of this interface, it's going to see a blocking mode. So logically is blocked, but physically this on and this link is still on. But logically in a blocking mode. It's very, 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 very important to understand that concept. So, as we say, one logical path between all destinations on the network by intentionally blocking redundant paths that could cause a loop. When a port is blocked, user data is prevented from entering or leaving the port. Okay, again, we're blocking it from passing what? Data. But still, this port will receive what? Remember that what we talked about the earlier B like boy, bridge, protocol, data unit, BPDU. Okay? This is like something internally, something to do with the spanning tree for all the switches to communicate. It's like we send like it's like a message. Are you there? 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 Constantly. That's basically what the PBDU is for. Okay. Any question at this point?
Nope.
Awesome. So a block port has the effect of making the link a non-forwarding link between the two switches. This is create a topology where each switch has only a single path to root bridge. So as we saw on the packet tracer, what happened? Okay. You can watch that video and see. And that's what I'm interested in the operation. All right. That's what's going to happen, the steps. What's happening the minute you add that link? Okay. Um, Using the STA. What's the STA? Again, stand for? Spanning tree. What?
Algorithm.
Algorithm. So the first thing we need to do, remember we said we need the reference point. We need to elect the root bridge. So let me see if I can make this a smaller. Oh, okay. I don't know what happened to my. All right, I hear. So when this boots up, and say, man, he looks at himself and said, okay, it's good to be a king. So I'm gonna be the root bridge. And this one boots up, I'm gonna be the root bridge. And this is boots up, I'm gonna be the king. I'm gonna be the root bridge. Then when those guys start exchanging what they receive, BPDU, okay? So what's in the PBDU? They have something called router PID, bridge ID, which is BID. The BID consists of two things. It consists of the MAC address of each switch and also has a priority number. Okay. So based on this two information right here, you know, see that, the PBDU? And, and that's what we're talking about. During STA and STP functions, switches use bridge protocol data units that we're talking about to share information about themselves. and their connections. PBDU are used to elect the root bridge, root ports, designated port, and alternate port. So basically, the PBDU is going to help to create or to indicate which one is the reference point, which one is the root bridge. Because once I decide the reference point or the root bridge, I can decide later which link I need to block, where I want to block it, to which port. Okay? So, the main purpose of the PPDU also to help us to what? Elect that root bridge. So they can exchange information. And the PDU contains a bridge ID. So they have a bridge ID, the PID, that identify which switch send the PDU. The PID is involved in making many of the STA decisions, including root bridge and port roles. So the question is, what's in the PDU, on the PID? It's gonna, like I said, that's what they say here. The PID contains a priority value, the MAC address of the switch, and the extended system ID. We'll talk about this one in a few seconds. Well, let's talk about this one first. Priority value, like for example, I think they have some kind of 32768, that's by default. So all the switches by default is going to have the same priority value, which is 32768, if I'm remembering correctly. Then the MAC address, and then the MAC address of the switch. So the switch that has the less priority value and less MAC address, that's the switch that's gonna be what? The root bridge. Well, I just said by default, all these switches, they're gonna have by default, it's gonna have equal number of a priority value. So it's gonna be in other words, they all have the same priority value. So who's gonna bring the tie? If all the switches has the same priority value, what field is different then? What's gonna be different?
The BDPU. The
The
BDPU.
MAC address. Because we know we cannot have the same MAC address on any device. So the switch has a less MAC address is going to be what? The root bridge. So, in your opinion, if I bought a switch like 5 years ago, and I bought the switch 2 years ago, and I have a new switch like 2 months ago, which switch is going to have the um, lowest MAC address?
The 5-year-old one.
Yeah, the older switch. So can you imagine if I'm applying redundancy and I have a switch I bought 6 or 7 years ago? Well, guess what? That switch is gonna be the what? The root bridge. And if this is the
Is
switch,
that because,
go ahead.
they expect you to base it off of the oldest existing hardware for scalability?
The actually is not, because it's by default. This is how because the less the value you're gonna learn from now on, and this is from all the protocol, always they look for the less value, less cost. We're going to take the route for the less cost. We're going to take the route, we're going to elect the bridge for the less priority and less MAC address. And this is the main thing in here is, okay, you do not, I repeat, you do not plug in your network any device as a default. Okay. So If you think you have a beefy switch, and most modern switch has a better processor, has better memory, for God's sake, you need to go and change the priority value on that switch to make it the root bridge. You don't leave it as a default. And that's why most of the common issues with security today is misconfigured devices. Because I don't know, it's a laziness or less knowledge, people not knowledgeable to go and reconfigure that switch before they put them on the rack. Because as I said before, the switch by default, if you plug it, take it out of the box, plug it in, plug some devices to it, it's going to work. But that's not recommended. You always need to what? Configure it. Okay. So if you have some switch in mind, you want to make it as a root bridge, then what you need to do is you need to go and change the priority value. And the priority value goes from, it's a multiple of 4096. So if you put a priority value for a switch like a 0, whoa, this is always going to be the root bridge forever, you know, because this is the lowest priority value you can have. So, but I said, all the switches by default, they have 32768 as as a priority value. So if they all have the same priority value, then the only element is going to break the tie is the MAC address. So it's better to go to the switch and configure the priority value. Now, they talked about here extended system ID. So sometimes when you go to, you can see the priority value, let's say 32768, but the value's 32769. So what they add here, they add the extended system ID. The extended system ID is basically the VLAN ID. So they can add the VLAN ID to this value right here. So if you're connected with the VLAN and at 1, for example, they're going to take 1 and add it to the priority value, which is 32768. So now the priority value is going to be 32769. Follow? And so on. So, and that's what we say. Lowest BID value is determined by the combination of those three fields. 1, 2, 3. Any question at this point? That's what we talked about. The default priority value for all Cisco switches is the decimal value 32768, like we talked about earlier. And it's going to range, the ranges is 0 to 6114, increment of 4096. And the lower bridge priority is preferable. The lower bridge priority, whatever bridge priority is going to win the election, is going to be the root bridge. And that's what we talked about, the extensible, the extended system ID, basically identify the VLAN, okay? And of course, we have the MAC address, those three fields that we're talking about. Okay, so look at this. What we have here, we have, let's start with S2. S2, the bridge ID, if you notice, has 32769. Okay. And this one, 3269, because by default, we talked about the priority is 32768. Why this one has 69? Because of the VLAN ID. Okay. And the MAC address is 00A000111111. We'll go to the next one here. So this is less than this. This is 1, this is 122. But they have the same priority value. Well, we'll look at this guy here. It has a priority of 24577. Do you think somebody came in there and changed that, or it happened by default? No, somebody did his homework and he decided to make S1 as what? The root bridge. So this is the root bridge based on the priority. And the reason why, if you look at the MAC address really is the largest MAC address from this one and this one here. Now, why this guy became the root bridge? Because it has what? It has the lowest priority value. Okay. So when this is boots up, his thing is the root bridge. Then this guy is gonna send them a PDU to this guy. This guy's gonna think he's a root bridge one. After he receive the PDUs from S2, say, oh, I was wrong. So you are the root bridge. Then receive this one from S1 and so on. Said they after they exchange all the PDUs, then they come to a conclusion that S1 is the king. Here's the root bridge. Here's the reference point. Once we determine the um, reference point, then the port that's linked to the reference point, it becomes the root port. So this guy here, the F01 becomes the root port. Why? Because the port is connected to the root bridge. And this one here is F01 is connected to the root bridge. Then this is going to be the root port. You follow? And all the other port is going to be designated port. So we're going to have designated port for every segment. Means what? This is going to be designated port. This is going to be designated port. Now we have here an issue, okay? So between F02 and F0 slash 2, who's going to be the designated port? So that depends on the link, like you said, the speed of the link. If all of them has the same speed, then whoever has the less MAC address is going to win. So this is going to win. We're going to block it right here. You follow? And that's how it's going to work. Does that make sense? No, does not make sense. What do you think? I think we talked about this one. Same thing as this one. Same. We already mentioned that. Now, one thing you need to understand the cost of the bandwidth. So if you have a link, between, like if you have a link at 2 gigabit, a 10 gigabit, then the cost is going to be what? It's going to be 2. If you have 1 gigabit, it's going to be 4. If you have 100, it's going to be 19. If you have 10, it's going to be 100. So the less the value, the better the path. Okay. And this is based on the 802.1d. Okay. The cost, which is that's the oldest protocol. Then on the new ones, which is we call it a rapid STP. That's a new version of STP. From the word rapid means what? Faster. It said, well, I don't need to wait 60 seconds to send and block and all that stuff. So that's the value for this particular protocol, which is introduced in 2004. Okay. Okay, so let's see what happened here. As you can see, this is the root bridge. This becomes root port. This becomes root port. And this is like we have a path path 1, path 2, path 2, right here. So everything going through the cost. Now, if this link right here between this one and this one is slow, let's say 4K, and this is like a 10 gig, then we're gonna block it here and go this way, okay? So this is where the speed plays the issues. Where are we gonna block it? And that's what they say. After the root bridge has been determined, the algorithm is used to select the root port. Every non-root, which will be select one root port. The root port is the port closest to the root bridge, which is this. What did I say? The root port is the port closest to the root bridge in terms of overall cost to the root bridge. This is overall cost is known as internal root path cost. Okay. Anyway, we got the idea. Now, once we determine the root port, then the rest of the ports are designated port. We're going to have one designated port per segment. So this is a segment, this is a segment, and this is a segment. So that's why once we determine, okay, this is my root port, then automatically this will become designated port because that's the segment. So we have one for per segment. This is for this segment. Now over here is for this segment. That's the port for this segment. Now, once we determine this one for this segment, then what we're going to do here, we're going to block it right here. And this is going to be blocked right here. Okay? And that's, we call it the alternate port. So F0/2 is the alternate port. Okay? Okay, any question at this point? That makes sense?
I had a question.
Okay.
We go to your packet tracer thing that you have like to try some.
Speak up, I can't hear you. Who's this?
This is Brandon. Can you hear me now?
Yeah, better.
Okay. Can we go back to your packet tracer?
Okay.
Between switch 1 and switch 2, can we change that to a fast Ethernet instead of the gigabit 01? I want to see what it does.
Between switch 1 and what?
And switch 2. Being that it's a gigabit speed right there, if we
Okay, so
change
you
it
want
to
to change
fast
it to.
Ethernet, will it?
Okay. Oh, is that what you want to do?
Yeah, and change it to a fast Ethernet.
Okay.
So it still retains the, even though the speed of the connection changed, it still reserves that alternate port on switch 0.
Yeah, you know why? Because it depends. First, we need to. The speed has nothing to do till we elect the root bridge. Once you elect the root bridge, what the speed is going to impact is the root port. Which one
Gotcha.
has the least cost to the root bridge? You follow?
Okay, I understand.
Good question. So in the process, step number one, we need to elect the root bridge. So we discussed the three criterias that basically makes or elect the root bridge. We talked about the PID, which has a three field, the priority value, the MAC address, and the VLAN. Okay. So by default, all the switches has a 32768 priority value. So the only thing because at this time, they all ties in the priority value. They have the same value. The only thing can break the tie at this point is the MAC address of that switch. Unless if you go to the switch and you lower the priority value from the default, okay, and that's what did on the S1. Somebody went there and changed the priority to whatever they put, less than 32768. Then S1 became the root bridge. Then after that, we need to determine the second step. We need to determine which one is the root port. How are we going to determine the root port? So the root port, basically, we're going to say find the best path to the root bridge. So which one is the best path to the root bridge? Based on the bandwidth, the lowest, like for example, cost. So after we determine the root port, then we're gonna, all the ports is gonna be what? We're gonna call them designated port. We're gonna have a designated port per segment, okay? So after we do that, we need to have, uh, we know where to block or to have what we call the alternate port, okay? Make sense? And that's what we're gonna
Yes, sir.
block it right here. So doesn't mean if it's blocked, it's not receiving a PBDU or a BPDU. So they always have communication between S2 and S3 every 2 seconds about a PBDU. But the only thing we're blocking from forwarding data or information. Electing a root port from multiple equal cost. Okay, so that's a good question. So when a switch has a multiple equal cost pass to the root bridge, the switch will determine a port using the following criteria. Lowest sender BID, lowest sender port priority, lowest sender port ID. So that, let's say we have a port F0/9 and another port have F0/2. So therefore, 2 is less than 9. So therefore, this is in case we have equal costs. Okay. And also the MAC address has to play because the lowest sender BID means what? The bridge ID. The bridge ID consists of what? Consists of MAC address and priority ID. So the switch would, this is an example here. All right. So let's see. This is the root bridge. I am right here. So what's the cost here? Let's say the cost is 4 here, 4 here. So from this point to go to the root bridge, it's gonna cost me 8. Well, at the same time, if I'm here, and this guy I'm going to here, well, it's the same cost. Okay. So I can go this way or I can go this way. So why we cannot break it here? We broke it here. Now let's see. This priority ID 32769 55555. And this is 367068. 69, which have the same one. And have A. It's a hexadecimal. What's the A in hexadecimal? It's 10, right? So this has less. So therefore, we lock it here, open it here. And the reason why, because we have equal cost. Let's see what they say here. This topology has four switches with S1 as a root bridge. We already know that. Port F01 on switch 3. This is what? And port F03 on switch 4 has been selected as a root port. Yeah, because this is the closest to the root bridge. Selected as a root bridge because they have the root pass cost to the root bridge for their respective switches. S2 has two ports, F01 and F02, with equal cost passed to the root bridge. So the bridge IDs of S3 and S4 will be used to break the tie. And also this is like, okay, so this is known as the sender's BID. S3 has this BID, which is this is the priority value, which is same value as S2, but has MAC address 5555. And S4 has 32769, which is same thing, but has a 11. Okay, but because S4 has what? A lower BID. Is it S4 has less? Ah, I see what you mean. Okay, so S4, what are you talking about? S4, which is this, has a lower BID. The port F01 port of S2 right here. Ah, okay. You see over here, it becomes a root bridge because this one has less value than the other one, than the S3. So therefore, we go in this way and not that way. So that makes sense, which is the port connected to S4 will be the root bridge. You follow what they're saying here? But how they determine this is 1111? This is my question. Oh, I'm sorry. Yeah. What is S3? Ah, yeah, S3 right here. So they compare the path between this and this. This is lower, okay? Therefore, we open it that way and we close it that way. That makes sense? Okay, how are we doing on time?
Yes.
How much time we have?
Went over.
Went over 1 minute. That's okay. Okay, so we'll resume tomorrow at the same time. Go ahead.